Okay, hi everybody. Here we are at section 2.4, a concept called elementary matrices. And this is something which is going to just blow the roof off of what we've been doing. So we learned, of course, that if you want to solve a system of equations, or you want to put a matrix into row echelon form, you could either interchange two rows, multiply a row by a non-zero constant, add a multiple of row to another, or this is something we've already established. And we're going to um, define now something called an elementary matrix. So an elementary matrix is a matrix that can be obtained from the identity matrix by a single row operation. Meaning you start with the identity matrix and either interchange two rows or multiply a row by a non-zero constant or add a multiple of a row to another row. But only one of those things. If you start with the identity matrix and you do just one of those things, the result you're going to get is called an elementary matrix. And let's look at some examples here. So we want to know which of these are and which of these are not elementary matrices. Well, if you look at A, we see that what did I do? I multiplied the middle row by 3. So I did one operation. How? A is good. Now, B is automatically, I'm not even going to look at B, because the fact that it's not a square matrix means that there's no such thing as elementary matrices. Elementary matrices have to be square matrices. So B is out. C, if you notice, the bottom row is all zeros, but that means I started with the identity, multiplied the bottom row by 0, but that's not good, because it would have to be a non-zero constant in order to be considered elementary. D, I started with the identity and I switched the second and third rows. That's great. So D is good. So far A is good and D is good. E looks great. It looks like for E, it looks like I multiplied, I added double the first row onto the second row. That's fabulous. So E is good. And for F, well, F looks good, except that it looks like it did two things. In other words, I multiplied the second row by 2, which is an elementary operation. And I multiplied the third row by -1, which is also an elementary operation, which is fine. The thing is, I had to do 2 operations, not just one. So even though F is like fine, but since I had to do 2 operations, it's not considered an elementary matrix. And this is really basically what the solution is. This is what they say here. So A is, C, A is, D is, and E is. B is not, C is not, F is not, which is just exactly as I explained just a minute ago. Okay, now, elementary matrices are really useful because they enable you to use matrix multiplication to perform elementary row operations. And here's an example of how that works. In the matrix below, now this is really key to notice this. E is an elementary matrix. What did I do to get E? So starting from the identity matrix, I switched the first and second row. Now I took this matrix E, which was elementary because all I did was switch the first and second row, multiplied it by some other matrix. And if you notice the result, if you do this matrix multiplication, you will see the result is this guy right here. But notice that the resulting matrix is basically is matrix A with the top 2 rows switched. So if you notice, the operation that I did to create the elementary matrix gets done to a matrix that I multiply it by. That makes any sense? And you also notice that in the next case, here I have 1 0 0 0 a half 0 0 0 1. So this is elementary because I just multiplied the middle row by a constant. and I'm multiplying by matrix A. Now remember that A is not a square matrix, but that's okay. As long as the elementary guy is square, I could still use it on any matrix as long as the size is such that multiplication makes sense. And as a result, if you notice what happened, is that I wind up, my resulting matrix is the same as my original matrix A, but the middle row is chopped in half. So the same operation that turned the elementary matrix, that created the elementary matrix, gets done to a matrix that's multiplied by the elementary matrix. I hope I'm saying that right, but I think you get what I'm saying. And a third example, here I multiplied I added double the first row onto the second row, and that's my new second row. So that's again an elementary operation. And if you noticed, when I multiply by matrix A, what did I get here? Well, the top row is the same. The bottom row, the top row is the same as A. The bottom row is the same as A. But if you notice, I have a 0 here. Why is it a 0? Well, if I add 2 times 2 to the negative 2, I get 0. If I add 2 times 0 to the negative 2, I get negative 2. If I add 2 times negative 1 to the 3, I get positive 1. And that is how this works, which is now, if you notice in all these examples, when we multiply E, E is on the left side. Because if you put E on the right side, you will not get this elementary row operations. What is interesting, if you do put E on the right side, you multiply A times E rather than E times, A times E rather than E times A, you're going to find that it does have a certain effect. And what it's going to do is that it's going to do the job on the columns. It's going to do the operation on the columns, not on the rows, which is kind of interesting, kind of very cool and interesting. Okay, so here's the theorem. Let F be the elementary matrix obtained by performing an elementary row operation on IM. If that same elementary row operation is performed on an M by N matrix, the resulting matrix is given by the product EA. In other words, this is really just saying this is just sort of summarizing what I've been saying this whole time, that whatever was done to create the elementary matrix, that's what the elementary matrix will do when it multiplies another matrix. Okay. Now, here we want to find a sequence of elementary matrices that could be used to write matrix A in row echelon form. Now that's kind of amazing, because when we did row echelon form previously, what we did is we would write these little notes. We switched this row, we added that row, we did blah 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 blah. Well, we just learned now that all of these operations can be expressed in terms of elementary matrices. So what we want to do now is look at what it would take to get this matrix here into row echelon form, and see how I would, and instead of expressing it this way, see how I would express it this way. Well, the first thing we did here is that we switched the top two rows, row 1 and row 2, because we wanted to have a 1 up on top. We want to have a 0 here. It's perfect. So row 1 got switched to row 2. Well, the corresponding elementary matrix for that is this guy right here, because here row 1 and row 2 got switched starting from an identity matrix. Now, the next thing I did is that, that's done here, is that -2 times row 1 got added onto row 3, because I want to turn that 2 into a 0. And that became the new row 3. Well, the corresponding elementary matrix to that with this guy right here. And that's why I took -1 times the top row, added it onto the bottom row, and this is what I got. So again, this is just the corresponding matrix. Now, but everything we're doing here is going to be so awesome. And the last thing we're doing is I'm just taking row 3 and multiplying it by 1/2. And so 1/2 row 3 becomes the new row 3, but that is represented by this matrix right here. Now here comes the punchline. The resulting matrix, which is my row echelon matrix, is equal to the original matrix A that was up on, you can't see A now, but it was way up on top at the beginning of this problem. Multiply, instead of saying switch this, switch that, so do this, we're going to say multiply A by E1, and then the result of that, multiply that by E2, and then the result of that, multiply that by E3. These matrices right here, and you're going to get matrix B, which is our final row echelon matrix, and that is tremendous. So the moral of the story is that oops, the matrix that was our original A, is that the matrices that the row echelon matrices that we've gotten, we can express them as products of the original matrix times elementary matrices, and that is going to prove to be extraordinarily powerful. That is going to be very, very powerful for our purposes. Now, the two matrices that I had in example 3, this is matrix A, and that's matrix B. So since I got from one matrix to the other matrix by doing elementary row operations, we say that they're row equivalent. Since I can obtain matrix B by performing a sequence of row operations on A, then we call these two matrices row equivalent. And B, matrix B, as we said, is equal to E3 times E2 times E1 times A. Actually, I kind of started with A, and then I put E3 on the left, and E2 on the left, and E3 all the way on the left. And here's row equivalence. So if I can get from A to B by doing all these operations, then I say they're row equivalent, and I can express B as A times the product of row equivalent matrices. And that is a very, very powerful effect. Okay, and we're going to learn now that elementary matrices are invertible, and it's actually kind of easy to see that because the inverse of a well, let's just look at this. If here's my basic one is switching two rows. Well, the inverse is to switch them back. So actually the inverse is the same as the original thing, just switch them back. Here I have an elementary matrix where I add -2 of the first row onto the third row. Well, if you want to reverse that, just add +2 of the first row onto the third row, and that'll get rid of it. That's going to get rid of that 2 and turn it back to a 0. And here is my third elementary matrix where I multiply the bottom row by 1/2. Well, if you want to reverse that, just multiply the bottom row by 2 to double and just get it back to where it was. So we see that very simply, just with simple logic, every elementary matrix is invertible, and that is a very great thing, which means which means that if B is equal to these guys, like let's say over here, here's easier. If B is equal to these guys, then I could say that A is equal to, if I multiply both sides on the left by E3 inverse, and then multiply both sides on the left by E2 inverse, and then multiply both sides on the left by E1 inverse, and we're going to get that A is equal to E1 inverse times E2 inverse times E3 inverse times B. In other words, A can be obtained from B by elementary row operations. That is an extraordinarily powerful property.